and I'm going to share my screen.
All right. Yeah, that works. Can we go next slide? Perfect. Yes. So hi everyone. My name is Arvid. I'm not an expert on causal analysis at all. I sort of chose this paper because Peter assigned it to me, but yeah, there are a lot of things I am not quite clear about. So maybe we can have a bit of a discussion about this. I think it's quite interesting. So what is a paper trying to do? It's actually tackling a very, very common problem. You want to understand how a variable can force another variable. And this variable is typically called x, but there's another variable in the background that, at least on your historical data, would have caused either x and also your treatment variable, your outcome variable y. So it would be very hard to actually see anything. If you go next slide. now causal analysis actually can handle this problem in general. If we go to the next slide. I think it's just the buttons should be working. Yeah. So this is how the general setup is. We have x is causing y in some way, and we want to try to find out how that is and how much that is, or whether it is and how much it is. But we also have another variable z, and z could be here not just a single variable, but it could be like a vector variable. So it could be a lot of things that affect x and y at the same time. And this is called a confounding variable, and it's generally, if we were to ignore it, we would get wrong results for all sorts of reasons. Now, how would causal analysis try to solve this? If you go to the next slide, please. There is a procedure how to solve it. Essentially, if you want to know how x affects y, we would cut down all the arrows that go into x, because now we are the ones that are controlling x, so we don't have to, there's nothing else forcing x anymore. And then we have to sum over all the remaining free variables that are not y, so that are ultimate parents of y, as confounding variables, and check how x affects y given each set of z coordinates. If you go to the next slide, that should hopefully make it a bit more clear in terms of numbers. These are the formulas. Essentially, yeah, how does y behave given we set x to a value summed over all the different values of z that we can observe in our data set, right? And if you think about these numbers are all something we would have in observed data, right? So at this point, we didn't do any experiment or so. It's essentially saying, given we know this sort of causal structure exists, so we have z, and z is influencing x, and z is influencing y, we can, in principle, from historic data, non-experimental data, figure out how y is affected by x, which is really cool, right? Because in a lot of ways, if you think about it, it would be impossible to do real experimentation, such as experiments on whether someone is smoking and whether smoking causes harm. It would be unethical to force people to smoke and check whether it has any impact on pregnancy results, for example. Now, what is one problem that might come up here? And that is I think, next slide. Well, what can happen is that z is not always directly observable, right? So sometimes you actually have another variable y that is sort of a substitute for z. And the question really that this paper tries to answer is, can we, if we have this new variable, which is not our hidden confounder directly, but a function of it, can we use that one to still do our causal analysis, essentially finding out whether x affects y, and if so, by how much, given this new observable w. You go to the next slide. And this is how this looks in terms of graphs. So we have x, y, and z again, but this time z also causes w. W is our proxy for z. And right away we can say, if we were to observe w, we would, under very strict rules, not be allowed to infer how X causes Y, just because if you're somewhat familiar with these rules of causal analysis, knowing W does not block the information flow from X to Y via Z. So the spector path is not closed. So that would mean we could still, from that data alone, by confounding on W, we would not be able to tell how X and Y causally relate to each other, which is unfortunate. But if we, next slide, please. If you think about, maybe we can do still something with it, because if you can do a thought experiment, right? So imagine W is an exact copy of Z. Next slide or next click. Then we know, if we know W, we do know Z. And then this way, Z would have been exactly blocked. And then we know for this case, if Z is blocked, or if you observe Z, then we can definitely tell the effect. So that raises then the question, what's, if we have this on the one hand side, is this very clear observable relationship where W would be equal to Z, we block it. And otherwise we replace that with a noisy relationship. Can we still infer something from it? Next slide. And that is practically quite useful, because often you can have separate studies that study how a hidden confounder relates to an observable. You can think of physical experiments, say that would be very costly, but you could get some sort of curves or so that would tell you what this relationship is, and you could always put in a lot of effort to measure these more exactly. For example, if you, I don't know where to look for some relationship between smoking and lung tar, you could do experiment on how lung tar, which is something you might not be able to directly see in a live patient, but you could relate, for example, how this lung tar would relate to blood pressure, which is something you can on some biopsies do. And so you could potentially get, via a completely different study, results that you can then transfer back to your original question of how does it actually work for the overall question, is smoking harmful or something like that.
Arvid, before, what did you mean by information can still flow from Z to X, and so you can't recover the the causal effect?
Essentially, if you go back one slide, right, in here, what can happen? So you could see, if imagine W is completely unrelated to Z, right? So say, and Z, let's try to take an example. Let's say X is you're smoking, Y you get cancer, right? So now and Z, let's say Z is a confounding variable. Say Z is, does the person live in a region where people smoke a lot? But it might also be a region where people have naturally higher cancer. Maybe it is some place in some part of the world where there's a lot of pollution, and they have very lax very lax standards of smoking. So now this would be a hidden confounder. So if I know someone comes from that country, then I wouldn't know that they have a higher risk of cancer to begin with, also more likely to smoke. But if I had this in the background, and I would have two groups of people coming from that country and people not coming from that country, their X and Y values would be correlated, right? Because people, when they come from, when they have cancer, they're also more likely to come from that country that is more prevalent in smoking because of cultural habits. So this hidden confounding essentially allows for correlation to build up without there being a direct causal link. It's actually quite interesting, this whole causal analysis. You often hear correlation doesn't imply causation, which is true. However, correlation does imply there's a causal path of some sort. It might not be a direct causation, but there's at least a hidden confounder that would explain that, which is actually makes this correlation implies causation somewhat less trite if you think about it, which is quite nice. Does it answer the question?
Yeah, I understood the explanation. I guess I didn't. Maybe I asked the wrong question. I didn't understand how you can cut the link between z and x in the previous example that you gave.
Well, if you well, yeah, good question. So what does confounding mean, right? So if I were to do analysis and I would know about these two countries, so one country people smoke a lot, people have a higher chance of cancer to begin with. But of course, in that country, not everybody is smoking. So if I were to look only at data from people of that country, I could still compare people that do smoke and people that don't smoke. In this case, this treatment, is someone smoking or not, would be essentially randomly assigned, right? Because they are very similar. They live in the same cancer-ridden environment. They live in the same smoking culture, yet some people do decide to smoke, others don't. So we could argue this is essentially a random link because there are no other confounding variables we are at least aware of. And in that case, if you look at this country specifically, you would see actually a negative correlation, a positive correlation on top of the background value, right? So that would be an example of cutting the link. And of course, we would have to do the same thing for the other country that doesn't have this relationship. And it's an example of Simpson's paradox, essentially, right? So Simpson's paradox means that if you have these confounding variables, sometimes your correlation could go the opposite direction just because this confounding could happen in such a weird way that that's why this path analysis is so important. And so cutting actually means more of a methodology base. So if I have any structural diagram like this, I want to know what happens, I cut it and I cut all the incoming arrows into X and sum over the others. But of course, that is just a prescriptive step of how I can translate a graph into a formula that I can then actually calculate from real data. Okay.
That makes sense. Thank you.
Awesome. The next slide, where was it? So yeah, the idea is, okay, we know, if we know how Z and W relate, we can, given W, know something about Z. And the question now becomes, given we have this relationship there, can we still infer causality of some sort? That would be great, right? Because in reality, that is probably a very common case. We very rarely can observe confounders directly, but if we can relate it, suddenly a lot of problems open up for us to be solved. If you go to the next slide. And so what did Pearl do? First of all, we have to assume that the observable only depends on the hidden confounder. This is not strictly necessary, but makes a lot of the calculations a bit simpler, because otherwise we'd have to carry an extra index, and then we have to be very careful in essentially calibrating the curve, how W behaves when Z changes only for each value X and Y, which would make things even harder as they already are. Next step, please. And now the idea is that a relationship can be invertible, right? So I took a little bit of a liberty here, because he only talks about an invertible relationship, which sort of suggests that there must be at least as many different W values as Z values. But on the other hand, I'm not quite sure how strictly necessary that is. Here I say, okay, if I know the transitional probabilities between Z and W, if I observe a particular value of W, I know what the underlying probabilities of the Z's are, right? That is standard statistics, and a priori they don't have to be the same number of observables, right? And the idea is now, okay, if they were the same dimensions, we could actually invert it. If you go to next slide. Yeah. And so the idea is, if you go to next slide, that anywhere where we have Z in our formulas for our classic causal problem, right? We have the formula, we know what the exact formula would be if we were to know Z exactly. Now the idea is to replace all the instances of Z with W by using this inversion equation. And technically, this also could hold for continuous problems, right? So where Z and W are maybe not discrete values like categories, but rather a continuous function. You could still invert a Gaussian, for example. If I observe a value of Z of 1.256, this would relate into a probability distribution over W of some sort. Okay.
Arvid, can I ask a question here?
Yeah, please.
So instead of assuming m equals n,
I think so.
Actually, can I see the previous slide? Because the way you invert. No, sorry, the matrix is WZ.
Yeah.
And then you switch the positions from Z and W. Can you assume that this new matrix you have here is an inverse of the previous one?
Generally not, right? So if m and n are unequal, then that wouldn't work. But I definitely, please correct me if I'm wrong, but if I talk about the statistical problem, I can always relate my probabilities of Z to probabilities of W. And this is where I get quite confused, because he never really belabors that point a lot. He just says, oh yeah, it's invertible, so invert it.
Right. So maybe when you assume it's square matrix, it makes the inversion a bit
yes.
easy.
Yeah.
And you assume all p's are independent, right?
Yeah. So that
Which
is
makes the matrix invertible, because if they're independent, it's full rank, so you can invert it.
Typically, yeah. I think that the chance would not to be, there would be conditions where it would not be invertible, but generally yes.
So maybe instead, if you want to generalize, you can not assume m equals n, but you could say we solve this system. We assume there is a unique solution.
Yes.
And then that would be a more general statement, maybe.
I agree, and that is when we come to this is where then we could run into trouble. That's where this paper maybe falls slightly short, because it never really specializes what or specifies what exactly is needed for this to be still recoverable. So I think Pearl sort of assumes here that there is like a sort of approximate one-on-one relationship between W and Z, and they're just slightly noisy. And later in the toy problem, at least in the discrete case, we see that as well. He has such a problem. I don't know why his derivation, which would not work also with approximate or with purely statistical replacements of W and Z.
And probably in practice, you would end up doing some sort of these squares, and then it should be fine.
Yeah, the question would be, for example, then what happens if we have 4 observable Z? So Z could be one of 4 values, but we would ever only be able to observe 3, and the 3 could be a mixture of that. Could we still recover the original effect? And honestly,
you will have to make an assumption. For example, like a common one is sparsity, right? You would have to make some sort of assumption, or maybe assume if the Z's are dependent on each other in some way, and then build theory from that. I would think. Yeah. Because if it can be anything, then yeah, you can't recover it, right? There are infinitely many possibilities.
It's and that is where it's interesting. At what point do you lose this recoverability? If you go to the next slide, I try to actually, so this is still the standard derivation, right? So you take the causal equation and you put in the inversions. If you go to the next, so just the definition of replacing Z by any sum over W. Now here in this in the original paper, actually he doesn't call it PZ of W. He calls it IZ of W. But it of course has the form and interpretation of a probability. Here I just made it into a probability, knowing that this probably would not necessarily hold. So let's assume for the time being that Z and W have the same dimensionality, and this is an inversion in the classical sense that we have a square matrix we invert. Then I'm pretty sure this works guaranteed. I'm not sure at what point this would break down. Go to the next slide.
I have a quick question.
Yeah.
So couldn't you just find this like inverse matrix, which really was, it's an inverse mapping. Like it's an inverse matrix, but like in all the cases you point out where the support of Z is not the same as the support of W, then it's not like a square matrix.
Mm-hmm.
I think if you have Z given W, you can recover W given Z by, he says that like Z given W is a matrix where each column's probability sum to 1.
Yeah.
But I think well, my question is actually, if you just take each row and you normalize by row,
mm-hmm.
would you get Z given W given Z? No, Z given W, because we have.
I think so. Yes, at least in the square case that works, and it's actually quite interesting later if you look at the toy example, we see that his toy case does break down if the variables are mixing too hard. And so rather than this being an either or, I believe there must be somewhere something in this relationship between Z and W that makes it just recoverable or just not recoverable. Interesting, we also later see in the continuous case, essentially it becomes always recoverable, no matter how big the noise to signal ratio is, as long as there's some signal left, which is slightly bizarre, but probably at least approximately correct.
Hi, Arvid. It's John here.
Hi, John.
Hi. Yeah. Just quickly to go back to that point about inverting PZ given W to PW given Z or vice versa.
Mm-hmm.
I mean, you can do that if the priors are uniform.
Yes. Yeah, I think so. Yeah. So then if the uniform, the prior is uniform, right? Then what does it mean if you observe one W? Then so if there was no relationship, then one W just means you have all the Z's are equally likely, right? So that would be a sort of inversion, but at the same time wouldn't carry any information, right? So actually, if you go to the next slide, I did try this as an example where. So this is actually first of all, sorry, I'm jumping now, but this is the formula he comes up with that we have. If you go back one step here, so in his paper, right, he replaces this PZ of W with this inversion formula IZ of W, which behaves like a probability, but is, I think, something slightly different, and I'm not quite sure what exactly it is. Anyways, if you plug it in, you get this equation, and he argues that this is a correct equation. So John, what was your point again? Can you explain again? I think John raised the hand.
John, I've allowed you to talk, so you can just unmute yourself if you want to say something, or if you just want to type it in the chat or Q&A, you can too.
He would like to talk. Headset stopped working. Well, then let's try to go on when he's back. We can pick up the discussion again. So anyhow, if you put it into a formula, use these inversion relations, which you can technically measure outside of your original data, or you could even guesstimate it from the data, you get this formula, which essentially contains all observed quantities, right? So you know all the W's, so that's observed, you know how often W and X and Y co-appear in your data set, so you can count the probabilities, and you know all the PZ of W from your experiments, and then you can technically calculate this, and that should recover your effect, at least unbiasedly so. The question is, how good is it? That, I think, was the next slide. We have there are a couple of points of why this might not be perfect, right? So on the one hand side, if you think about it, we have now a lot more sums over a lot more values, and if you just click a little bit, oh, I think the arrow key could work as well, right? So we have now more sums, and that always increases your noise essentially, and if you remember, W could be potentially a very high dimensional space, right? So there is going to be a chance that some of the cells, as they call it, can still be very lowly occupied. Not many numbers in there. So that increases your problems even more. Another click. Yeah. So sparse counts, and another click would be that. Another click, please. Yeah. So we are estimating the denominator, and of course, noise in the denominator is even worse, because noise on a very small number could potentially really screw things up. So you would need a lot more data in order to still have a sensible estimate. So that was a question. Mahid wants to ask a question. Can you unmute him?
So I think now that you're allowed to talk, you just unmute yourself. I don't have control over whether you can unmute yourself or not, Mahid.
Hello, Arvid. Can you hear me?
Yep.
Cheers, Peter and Arvid. I might have misunderstood the paper. I'm not really an expert in causal relationship, but when I had a single look, I didn't read it again. I thought that once an event gets transformed into another, for example, if we want to establish a link between event X and event Z, and let's say the matrix of the former gets transformed with AX equals B. If that transformation leads to a matrix whose determinant is not zero, i.e. singular or degenerative, such that you cannot recover the former matrix using inverse, I had this in mind that this would mean that that event is not reversible.
Yeah.
As in if smoking causes cancer, cancer cannot cause smoking. That's what I thought. Is that correct, or did I misunderstand it?
Here it's about the relationship between the Z and the W. So Z is your hidden confounder, the thing you can't see, and W would be a approximate representation of that. And so it's that link that we're trying to formalize here, and which he calls being invertible. If you can imagine, if each value of Z has exactly one value of W, then it's a perfect relationship, and then W is essentially Z. And if we know W, we know Z. The moment we make this a little bit weaker, if there's noise in there, then observing one value of W could mean there are under the hood actually several values of Z that are possible. And it still becomes, and that's then, what does inversion mean? In this example, it looks like the inversion looks exactly like this probability inversion, that I know this event is probability 1 leads to probabilities of Z being a half, a third, and whatever that the rest is. But this interpretation of taking one probability and splitting it up into subgroups of Z does generally not have to be invertible to be calculated, to be able to have it, right? So even if there is no relationship between Z and W, we could come up with such a relationship that if we know any value of W, we can infer probabilities of Z. And the question really there is, does it have to be square in order to be useful? And if not, at what point it doesn't? And I don't know the answer. So Pearl really glanced over this. He was very hand wavy about, yeah, it's invertible, so we call it I of Z of W. That's it. Not making use that I is actually a probabilistic matrix at all. I'm sorry, I don't know whether that answers your question, but I'm probably just as confused as you.
Well,
One thing
to be fair, this is the only paper I've read on causal inference. So I guess with more reading, perhaps the way of I think the thing that's confusing me is how these causal relations are explored along the graph. I guess with more reading it'll come.
Yeah,
But your slides are very digestible, very easy to.
Thank you.
It makes this process very easy, I would say.
Yeah, there are a couple of really good books on causal analysis that I haven't explained why the do methodology or do calculus is as it is, and there are probably ways of deriving it. It might also be hand wavy, but I didn't go into that at all. But that can help understanding the whole problem a little bit better.
It is a fair answer, I think.
But one of one of the assumptions of the paper is that you already know the causal structure of the problem. And later in the paper, he talks a bit about how you can identify it, but it's given that you know the causal structure of the problem, how can you quantify the effect? So I think that's one thing to keep in mind about the analysis in this paper is that you already assume you know the causal structure. So both the graph and the structural equations.
That's a very important point Peter makes there. And I think that is quite generally. I read the Pearl book on this, and this is really, really good actually, because he makes it very clear that causal inference is something else from data science. You can't do causal inference with this data alone. You have to have causal structures. So it means you have to reason about things. And it's interesting because there are by now packages that claim that you can recover causal structures from data. I forgot. I think was it the Book of Why or something? It was almost like a popular sciencey book, but it was quite well written.
Just by chance, I started reading the Book of Why 2018 by Pearl on Friday. I'm not all the way through it, and yes, I'm pretty certain it's the book you're talking about. It's very accessible. I'd recommend it. Yeah,
exactly. And yeah, and his point is that data alone doesn't give you causal structure. So there are certain causal structures you can exclude given the data set, and we're going to talk about this at the end when we show that even under this imperfect conditions you can do some of these inferences. You need this input, and so that's why I'm very, very how to say, concerned almost that there are no packages that do claim to allow you to infer causal structures, which is probably wrong. And I tried it, and I saw also someone using it on benchmarks, and it failed spectacularly. And even didn't do the regular causal inference or the counterfactual analysis for effects very well. So yeah. Anyhow, so this trick he found here that we can use measurements that are not perfect to uncover real causal effects is not a free lunch in the sense that it comes with a lot of caveats. You have a lot more noise, and you have to probably have a lot of actual data to make it still work. And that is very important. You have to be very, very accurate on the relationship between your observable W and Z. If there's additional noise in that, it makes it even harder. And how much additional noise, that was not quite clear from his thing, because he just said, you can, as long as you can invert it, it works. The derivation doesn't break specifically down when it's not directly invertible. So that's why I don't understand at what point it would break down. If you go to the next slide, please. Oh yeah. So that's what I mentioned. So what happens if we actually make an variable w of z that is completely pointless? That is if you go next slide, it's fine. A couple more clicks. So if we just say we have a observation, but that observation is completely random, and we have n values of z. So observing any specific w would just tell us it's out of the standard distribution of z. Now, if you plug this into the formula, we get just a standard. Next point, we get just the classical what is it? Conditional probability, and at some point doing this, we clearly lost causality. So that's where I would be quite interested in at what point. So what's a direct relationship between w and z, so that we can still infer something about causality and not lose anything. And here he says it can be exactly recoverable, but that probably means it has to be a directly invertible relationship, like literally a matrix that you can invert. For continuous relationship, I don't know the math enough to know what sort of conditions this would put onto those relationships. Okay.
I think the intuitive or explanation that he gives for this is like, if W provides information about Z, then you can create an unbiased estimator. But the less information it provides about Z, where in the case you're giving, it provides no information.
Yeah.
The higher the variance of the estimator.
Yeah.
So like it might be unbiased, but you need such a high number of samples to recover it because it's really not, there's so much noise in the measurement.
Yeah. Yeah, but what does some information mean, right? So if I map from 4 variables to 3 variables, I'm pretty sure I could create a case where I would still get information from a measurement without being perfectly invertible. Would this analysis still hold? I don't know. I really don't. And I probably should ask Pearl himself, just send him an email asking what do you mean? Would be quite helpful. Yeah, next slide, please. Another trick that was argued in what one can do is propensity scoring. Essentially, we talked about next click, please. Well, one thing that can happen is that your space of cells, so your W could be very, very large dimensional. Same for Z. Your confounder could, you can confound on a lot of variables. Technically, you probably shouldn't, but sometimes you do. You get a lot of different cells, and there's your curse of dimensionality, that some of those cells will be, you won't have any observations. So what can one do? And one trick that works in this, for this particular causal diagram, when the Z is all you need to understand the problem, is to take the propensity, so as a variable. So the propensity is the likelihood given any particular combination of Z values to produce to have a treatment, yes or no. So you could, for example, build a separate model that tries to figure out, okay, given these values of my confounder, how likely am I to have treatment? And this number is called propensity for treatment. And then I can group all my variables according to this propensity. So I group all variables, or all observations that have a similar propensity for treatment. And I can do that because of the causal diagram tells me it's okay to do, at least according to the theory. I don't know, don't have the derivation at hand. If you go for next slide, next click, you can calculate the causal effect with that. And he argues you can do the same thing with W as well, where you can create a propensity out of W propensities. So yeah, if you go to the next slide. Sorry, there's a P missing here. So this is the second to last equation. That is your classical propensity score. So L is your propensity. You sum over all observations that have a similar propensity according to another model, and calculate the attributional effect due to that. This is this P of Y given X and L, the propensity. And he argues that this propensity can be replaced by this expression there, where we did essentially the same trick. We just replaced Z by W, and now we can replace the propensity for Z with a propensity for W. But with the same caveats, of course, we have a much more complicated formula. We have to estimate all of these things, and all the estimates probably going to blow up in our faces if we do that not very, very carefully. Yeah, very well. Then he uses a toy example. So that is now an example that could be quite common in practice. You have two Z outcomes, Z equals 0, Z equals 1. And you also have two W outcomes, right? So 0 and 1. And so this would be the case where we have a relationship that could be invertible, right? Because we have exactly the same number of possible confounding values, and we have possible observation values. So it should be invertible. And so if you apply the formulas he has there, so we can do the inversion. If you're familiar with this matrix inversion, you will see this 1 minus epsilon minus delta is exactly the determinant, or 1 over the determinant. And so this is classic matrix inversion. And we see that this also breaks down at some point, right? So if we have these epsilon delta close to 1, then this inversion, even though we have a square inversion, of course becomes a lower rank, or becomes a rank 1, and then it wouldn't help us either anymore. So there is this point where if the variables mix too much, where essentially you can't trace back, or you don't have any information anymore which W is more likely to come from, you're going to lose the effect again. If you go to the next slide, of course this calculation extends, and that is actually quite cool. I don't know too much about it either. You can interpret these PZ weights as weights, right? So and you can essentially say that each observation you have, where we have, say, omega W being either 0 or 1, is actually two observations added together with different weights. And the weights they are added together with are exactly these weights for Z equals 0 and Z equals 1. And if you go to the next slide, I think we can mix these. And then he says, so depending on how PW behaves, if we know how the transition probabilities are, we can split any observation into different components, Z equals 1 and Z equals 0, right? And it's only if we can do this, we can in principle still observe it. If we observe P1 with too high a probability, then actually we know that our model must be broken, because then there's no way Z1 or Z2 could be, or Z0 and Z1 could be arranged within our understanding of how Z and W are related to still allow for the interpretation of a mixture of synthetic data sets. And what one can do is, once one has these observations, one could in principle create this data set of synthetic observation, can sample from that with their weights, and one can get information and can do all the sort of typical statistics one would usually do if one had a clear data set. So yeah, and based on your overall problem structure, this mixing factor is telling you how good it is, I think, and you want to be close, I think, to the sides, so that if you observe a site, a observable omega W, you want to be able to. It's better if you can assign this to a specific Z1. The more the better. And I think the moment where these two arrows, I think, become the same length, essentially meaning that you observe something, but you take your observation and split it equally, I think you lost probably already that sort of information, that because you can't recover this causal effect anymore. So you have to have a difference in splitting. That of course also means if this difference is small, so if there is only very little information in your transformation left over, you probably need a whole lot of data in order to make this small difference between your synthetic data groups actually show up in any real data set to have a statistically significant effect analysis. So that is another way of showing that, yeah, the less noise, the better, which is probably obvious. If you go to the next slide. Yeah, so this is the final formula came up with, and of course, if you put the epsilon and delta, which is your noise parameters, to 0, you recover your original formula, where W and Z are the same. So that is good. This shows that it is probably not too wrong. Okay, next clicks. Yeah, that's it. And next one. And he looks at another toy problem, which is these linear system of equations. So now W is the observable, and it depends on Z and Z only. And yeah, X is, again, only depending on Z, whereas Y depends on Z and X. There's always noise somewhere. And the task is to find out what is C0. So C0 is our causal effect on how X and Y relate, really. Next click, please. There's actually putting it into linear system makes it somewhat easier, because we can solve it directly without having to have the calibration technique. So we don't necessarily have to calibrate, as long as we have 3 independent proxies. So if you click again, I think. So if we had the case on the right-hand side where Z, it's still a linear problem. So all I said here is still applies. It has to be linear. But now instead of only W, we have a second variable V. So we have 2 variables that are linear related to our original observation. We don't even have to calibrate, because then we can use these relationships to essentially figure out the necessary statistics that are behind Z in order to calculate everything, which is kind of cool. Problem is, of course, most relationships are not exactly linear, but approximately so. So I think stuff like this is fairly commonly used in economics, for example. Okay, next click, please. So yeah, if you solve it, you get this relationship. Essentially, if you have noise, then the second term, the term after the minuses are something. Otherwise, it would be the pure the non-confounding case, right? Covariance X and Y over variance of X. It's this C3 squared variance of Z that is something that you still have to somehow infer. So that C3, if you remember, is how Z and W are related. So that would be the thing you would have to measure. And variance Z is also something you would have to measure outside in like a pilot study or in a calibration study. Again, if you have this second variable, that would fall out again, right? So if you have V available, then we can actually find out what is C3 square variance Z by observing how the covariance of X and V and how V and W are correlated. So we could take it out. Again, kind of cool. And then we get this formula. Yeah, I think that at this point it gets a bit boring because it's literally just looking at the raw formula. But and next slide, please. Yeah, if you don't have the luxury of having 2 variables, then we would still have to estimate C3 square variance Z, and that would come down to understanding which part, if you observe W, how much of its variance is due to Z moving, and how much of its variance is due to just the random noise, right? So we have to understand what is the signal to noise ratio in W, and if we have that, then we can estimate the rest. And next click, please. So noiseless case, again, it recovers to the standard calculation. So it's where exactly W is surrogate for Z. These, yeah, again, I don't know what to really say about these calculations. They are I guess, what they are. If we go to the next slide. If we add noise, we get these 1 over k factors in there. And those essentially, 1 over k is smaller than 1, so they become bigger and bigger. So we essentially add something that breaks. And at some point, even the denominator could actually diverge even at finite noise levels. If it gets too big, here we compare variance of the noise to the variance of W. And you can imagine if these are 1, then it means that essentially the whole effect of W we see is pure noise. So but at least at that point, everything explodes anyways, right? Because then 1 over k explodes and the whole thing becomes more or less meaningless. But technically, I think the moment we have anything that is smaller than that in terms of variance, so as long as there's some signal, we should be able to recover the effect, which seems crazy, but probably in reality, you would need that much data that it becomes just as well useless if you really were to push it. Yeah, next slide, please. Yeah. Oh yeah, the last point I think was structure testing. That is the interesting part about data that you can actually disprove certain diagrams, certain causal structures by testing whether if you allow for the confounders, whether they're independent or not. And he shows that this noisy observations that becomes a little bit more complicated, but still possible. If you go to the next slide. He has I think that's it. So next slide, yeah, next slide. So he has a theorem that, and I think it still needs that it has to be a linear system, but if you have a linear system with noise, then the covariance between X and Y is a function essentially of the covariance of your observable and all other observations. Yeah, Peter agrees it says to be linear. So for the most part, it has to be. I think X and Y don't have to be precise linear because you're trying to show independence. So if Y would be a function of X square, technically this would still hold, but I think the WZ have to be definitely linear relationship. And he just plugs in the values and says this formula is always fulfilled, and you can use this relationship between the covariance of X and Y to test if this holds true, right? Then if you go to next slide, please. Next click. Then so here you just this holds true if C0 is 0. Yeah. If you and one can use this. Yeah, sorry, next slide, it's fine. One can use this to essentially create a new variable, which is X minus this here, the W covariance XW over var W minus var epsilon. Of course, here the variance of W and the variance of epsilon W would be something you have to measure. So again, you need this calibration step in it. But if you have this, you can calculate this new statistics. And if your variables are indeed independent, then this new statistics should be independent of Y. So this is something you can test. And then even under this noisy assumption, you can still test invariance of the causal effect, which makes sense, right? Because if you can measure a causal effect with noisy variables, you can also measure that it is 0 and then use a statistical test on it. So it's perhaps not super surprising, really. And I think that's it. So if we go to the last slide. So yes, there are hidden confounders can still be exploited if we have observations, and even if they are noisy, but it makes things a lot harder. You click. So we can get asymptotically unbiased, but of course we need a large number of data, and we would have to have a very good control on the relationship between the hidden confounder and the observable W. If we don't have that, then we invariably going to create bias in there that makes it almost a pointless exercise. If you click again, I think there was something else. Yeah, so that's what I took away, that if we have two proxies in the linear system, We don't even have calibration, so that makes it a lot more useful. And we still can test conditional independence in linear system with these noisy measurements, which is kind of cool. I think that's it.
Thanks, Arvid.
Thank you.
That's a great paper. Thank you.
Yeah, and great slides.
shows us.
I think it's a very hard to digest paper.
Yeah, it took me a good amount of time, and I'm still not sure about when exactly or how messed up the relationship between W and Z can be to still be useful. And in practice, that might be actually an important question.
You can turn that on its head a little bit and say, so if you've got infinite data, you might be able to extract the relationship. And if we've only got some proportion of infinite data, we'll just be reducing the error. So if you have few points, you will bound the error that you can have, if that makes sense.
Yeah. So I would expect exactly that. So I would expect at some point when it's maybe not perfectly invertible, that you will have a bias, but you can bound that bias the closer your system is to being perfectly invertible. And then so you probably can't ever say anymore the causal effect is 0.35, but you can probably say something it's larger than 0.1 and smaller than 0.5. And I'm sure there's probably some papers out there that do something like that, but I haven't looked into that yet.
Awesome. The bit of the book that I've read, the Book of Why, meant that I had meant that I have a little bit of understanding, and I found that your talk really good, Arvid. So yeah, thank you
very much. I found another online resource actually that I'm looking at right now. I don't have the link close by. And let me 1 second. I put it in the chat. This I found quite refreshing. It's written by an economist, and I think he makes use a lot of the data, the work by the guys who just got this year's Nobel Prize or last year's Nobel Prize in economics. And then I'm working through that, and he makes it also a little bit funny, like memes and everything. So it's not as dry, but he doesn't shy away from the math either. So I think it's a nice resource.
Cool. I'm gonna stop recording.